Hi everyone, welcome to AP Environmental Science. In today's video, we're going to be talking about Unit 2, which is our Earth Systems unit. We're officially moving into content, and a lot of this stuff is stuff that you haven't really gone over or learned since middle school, so it is going to be a big refresher for a lot of you. So I highly recommend that you take down more notes other than what is on the slides. And if you need any help, please come find me. But we are going to be doing a ton of activities in class to help reinforce some of these concepts. All right. So for unit number 1, you can just skip it because I wanted to do that in class, but we're not going to be able to do it because I am not going to be in on the day that we were going to do this. So, as always, linked in the slides, I will have some additional information for you guys in case you need it as a refresher or to help with some of the concepts that we're going to be going over. So the first topic that we're going to talk about in this unit is plate tectonics and, the layers of the Earth and kind of what's happening inside our Earth and on top of it. So we have to know a little bit about Earth structure. So the Earth is 4.6 billion years old. It's composed of the following sections. So again, the Earth is a sphere. It is circular. It is a 3D object. It is not flat, despite what some people might think. And it's made up of these 5 main sections. So the innermost area is the solid inner core. It's a dense mass of solid nickel, iron, and radioactive elements that release massive amounts of heat. So the reason why, as you go deeper into the Earth, it is, really, really hot. And it's what keeps this liquid outer core right here liquid. Okay. So after that, we have the mantle, which is a liquid layer of magma surrounding the core, kept liquefied by the intense heat from the core. Then we have the asthenosphere. It's a solid, flexible outer layer of the mantle beneath the lithosphere. The lithosphere is this thin, brittle layer of rock floating on top of the mantle, and it's broken up into plates. And on the lithosphere, we have the crust. It's the very, very, very outer layer of the lithosphere, and it's essentially Earth's surface. So kind of imagine the Earth as physical plates floating on top of a movable liquid surface. So plates floating on water. So the plates would represent the crust and the lithosphere, and then the asthenosphere mantle area would be like the ocean. Okay. So because we do have this liquid layer of the mantle that again is heated by the core, we're going to have movement because liquid does move. So the asthenosphere is solid and it's flexible and it's sitting on top of the mantle. But then we have the lithosphere, which is this thin layer of rock that floats on top. And because it's floating on a movable outer piece, you're going to have shifting of that layers of rocks. And this is where we get something called tectonic plates. So tectonic plates are these massive slabs of Earth's lithosphere that help, Can I just get rid of my face? I don't think I can. It's kind of annoying. There we go. That help define our continents and oceans. So if you look here at this image, these black lines are diagramming how the plates of the Earth are designated or shaped. So these plates here are floating on top of one another and they are touching each other. Okay, so these 2 plates right here, they are touching. These 2 plates right here, they are touching. And this is important, and we'll get to that later. So let's keep in mind that the human race is relatively new in the grand scheme of things, and our knowledge about the Earth and the universe around us is still new and ever changing. So this idea that there even were tectonic plates is relatively new. So it was not always clear that the continents and the oceans of the Earth have moved over time. You guys might have learned about or heard of the word Pangea, which is that originating solid mass of continental crust of land that used to exist together hundreds of millions of years ago, that eventually separated due to the shifting of these tectonic plates on the asthenosphere on top of the mantle. So in 1912, this guy, Alfred Wegener, proposed the hypothesis that the Earth's land masses once existed together as Pangea, and eventually they shifted over time due to these tectonic plates. And we actually have evidence for this because of fossil locations and also just the way that the continents kind of fit nicely together. It is very interesting, but there is fossil evidence of the same species existing here along the eastern South American coast and the western African coast. So that is very interesting, and it is definitive, not definitive, but it is proof of this theory of plate tectonics. So this is now known as the theory of plate tectonics, which states that the Earth's plates are in constant motion, again, because they're sitting on a liquid, movable surface. So here we go. Here is the movement of Pangea over time, and this is how many millions of years ago it was. And here are the same fossil evidences that we can see. So we can find also the same rock formations and the types of rock and composition of rocks in similar locations that are drastically far apart today. So this, again, is a theory, but we do have evidence to support that theory. Okay, so this is where we're now going to get into, well, what happens when these plates are moving, and what kind of land masses do they form both in the ocean as well as on land? So these plates are moving because of the liquid mantle underneath them, and they're shifting, and they're, touching each other, essentially. And these can result in a few different things, and one of those things are earthquakes. So the plates can get stuck next to each other, and eventually they can give way, causing a quick motion. So if you have two plates that are like sliding next to each other like this, it is physical rock. And I mean huge, unimaginable slabs of crust next to each other, scraping against each other because they're next to each other. And they can get stuck and kind of locked into position. And once they eventually break way, there's a huge release of energy, and that is something called an earthquake. So they do happen very often, and they happen more specifically along certain fault lines, which we'll talk about in a little bit. They tend to be very small and undetected without equipment, and they're measured on something called the Richter scale. So the Richter scale measures on a logarithmic scale, meaning by a factor of 10 per each unit. That means an earthquake measured at a 6 is 100 times more intense than one measured at a 4. Okay? So again, earthquakes happen when plates get stuck and they eventually release, and it causes a huge burst of energy and, shaking of the physical ground. Hotspots are areas where the planet's core remains hot and surrounded by magma, and plumes of it well upward. A plume is just like a spurt or a burst of something, and welling upward means it's floating to the top. So when this happens, these create something called hotspots, where molten material from the mantle reaches the lithosphere. So here we have the mantle, which is going to have that liquid magma, which is heated by the Earth's iron, very hot core. And we have a plume, which is an area where the magma can shift upwards. And once it reaches the surface, when magma cools off, it becomes solid rock. Okay, typically metamorphic rock. My rocks are something I haven't learned in a long time. If it's not metamorphic, I'm so sorry. We don't really have to know the rock cycle in here, but I think it's metamorphic or igneous. I don't remember. I'll figure it out later. However, when this magma does cool, it will eventually form a landmass. Now, remember, these land masses are sitting still on that plate. So see how in this image the underlying rock is shifting this way? So when this magma comes up, it cools, it becomes an island. This island is still now sitting on the plate, and the plate is now shifting. The plume still stays in the same location because the plume's location isn't moving. It's the rest of the rock that is moving. Okay. So the rest of the rock is moving. And what is it dragging with it? Those islands that were formed by that plume. So this is actually how the Hawaiian Islands were formed with, I don't know how to pronounce that island. I'm not going to try it, okay? It's really embarrassing. But with this island over here being the oldest and the big island being the newest, okay? So these hotspots melt the crust, leading to a volcano where molten lava, ash, and gas are emitted. Hawaii has a lot of very active volcanoes. When earthquakes and volcanoes occur in the ocean, they can lead to a tsunami or a series of waves in the ocean that can cause massive displacements of water. So we've had some pretty serious tsunamis within the last few years. Okay, this we're not going to do because I just went over it. Okay. Boop, boop, boop. Ignore that timer. Boop, boop, boop. Skip, 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 skip. Okay, so now that we know about the core, the mantle, and the crust, we now have to talk about the plates and then what kind of crust can we have. So Earth is also made up of oceanic crust and continental crust, and it sounds exactly like they are. The oceanic crust is the crust under the ocean, okay, that makes up the ocean floor. It's very dense and rich in iron, and that's very important. The continental crust, however, is the one that's on land. It lies beneath land masses, and it's less dense, containing silicon dioxide. So if oceanic crust is more dense than continental crust, which layer would rise above the other if they were to intersect? So you have oceanic crust and continental crust coming together, because remember, the mantle underneath them is liquid. It's causing the crust plates to move in different directions. And we're going to have a name for those different directions in a second. So they're coming together, oceanic and continental. They're coming together, and it's going to cause one of the plates to go up and one of them to sink below. And the one that goes up is going to be less dense. The one that sinks below is the one that's going to be more dense. So the less dense one is going to rise up. The more dense one is going to sink. So if oceanic crust is more dense than continental crust, which layer would rise above the other? It would be continental crust. Why? Continental crust is less dense because it contains the silicon dioxide. Do you need to know what contains silicon dioxide per se? No. Do you need to know that continental crust is less dense so it rises above oceanic crust? Yes, you do. So I would definitely write that down. And we can see that here. So when these two plates come together, oceanic and continental, the continental is going to rise above because it is less dense. The oceanic will sink below. Oceanic and continental plates float on top of the denser material beneath them, and their slow movements are driven by Earth's magma that occur in the mantle. So there is this cycling of heat and liquid and solid, structures within the mantle, and it causes the subduction of the plate, and it's typically going to be the oceanic crust subducting or sinking. Again, why is this happening? Because the oceanic crust just happens to be made up primarily of iron, which is more dense than the silicon dioxide that's primarily in the continental crust. So when these tectonic plates, again, sitting on top of the mantle, are next to each other, which they all are, they form three different types of plate boundaries. Divergent means to come apart. So divergent plate boundaries move away from one another. Convergent move towards each other. And transform fault slide past each other. So the transform fault ones are the ones that cause earthquakes. Okay. This, unfortunately, we're not doing because I'm not in person with you. I wanted to do it in person. I'm so sorry. Skip. Okay, so divergent plate boundaries on the seafloor form new oceanic crust and result in seafloor spreading. Seafloor spreading. So when you have two plates diverging apart, that's now going to leave some space opening up where liquid magma from the mantle and the asthenosphere can actually come up. And when it's coming up, it's going to cool and form new crust. So this is how our seafloor is spreading. And this is the theory of how Pangea kind of split apart, because you had these plates drifting away from each other. The magma from the mantle was pushing up through the asthenosphere and then cooling and then causing the seafloor to spread apart, thus pushing the plates apart, causing the continents to shift. So divergent plate boundaries can produce volcanoes, earthquakes, rift valleys when they are on continental crust. And we can see that. This is a rift valley over here. So a rift valley on continental crust is going to form when you have the plates diverging apart, and you'll typically have water pushing in to fill in the space. Oceanic is what you're going to have one plate subduct underneath one another. Again, subduction is sinking or going underneath. It forces magma up from the lithosphere to the surface, forming mid-ocean volcanoes and island arcs, as well as offshore trenches. Oceanic continental is the one that we just talked about earlier, where the oceanic one is more dense. It's going to subduct underneath the continental. This, again, forces magma up from the lithosphere to the surface. And this is how mountains are formed, as well as volcanoes, trenches, and tsunamis. And then continental, one plate is still going to subduct underneath one another, but the pushing of it together is going to form our huge mountains like the Himalayas. Okay, I know that this is like a really long one, and I said they would be short, but I normally do this one in person, so I'm so sorry. I'm trying not to rush through it. Okay. Transform fault is when the plates are sliding past each other in opposite directions, and it creates a fault line or a fracture in the rock's surface. And then earthquakes are primarily going to result from transform fault plate boundaries. Pressure builds up as the plates get stuck, and eventually that pressure will release itself in a massive burst of energy that shakes the lithosphere and thus causes an earthquake. Okay, so this one you guys can do in your notes. Pause it here. Go ahead and do this. This is something that we would do in class that you can do right now because you need the color of the picture here. So go ahead and do that. Take a minute to pause. Okay, so the red lines represent divergent plate boundaries. The blue lines represent convergent plate boundaries. And what plate demonstrates the formation of a rift valley? The African plate, which is right over here. So how would we know it's the African plate? Rift valleys form on divergent plate boundaries. So we're looking for a red colored line. On continental crust, so we're looking for plate boundaries that are happening on continental land masses. And we got it right here. This we're not going to do right now. We'll do it later. And we're done. Okay. Sorry, I'm so used to teaching that in person and doing it with my Oreos. I am upset that I'm not going to be there. So if you're watching this for homework, make sure you have all the corresponding notes filled in. Feel free to write this in as well. Maybe try the other practice problems too, if you're feeling that. The work that we started in class on Monday, if you're in blue day and Tuesday if you're in a white day. Make sure you finish that because it's going to be due the next class period. And we're moving away from this and starting our soil series lab the next class period that I see you. So make sure you're prepared for that. If you need anything, please reach out, and I will see you guys all in class. Bye.